In this problem, we are to find all the zeros of the given function. Because this function is degree 3, I'm expecting to find 3 complex solutions. And I'm hoping at least one of the 3 complex solutions is a real solution and thus will show up on the graph if I graph it on the real plane. So let's go to our graphing calculator, press y equals, and type in our function. Now that I've typed in my function, I'm going to hope that one of the zeros shows up in the standard window. So I'm going to press zoom and then the number 6 to graph this function in a standard window. I'm seeing the graph cross the x-axis at about -1, -2, -3, -4, -5. Because each tick mark on the standard window is 1 unit, it looks like it has a 0 at x equals -5. Let me press trace, type -5, and then enter to verify that it is a 0. Notice when plugging in x equals -5, the output is indeed 0. So x equals -5 is one of our zeros. If you want, you can go to your window, change your x-min and x-max from -100 to 100 to see if there are any more real zeros to this function, and this is the graph that I get. So at least with visual inspection, it doesn't seem that this graph crosses the x-axis for any x values between -100 and 100, besides x equals -5. That doesn't mean that the other 2 solutions aren't real. They just may be bigger than 100 or less than -100. But since I know x equals -5 is a 0, we know that the function has a factor of x plus 5, which means that my polynomial can be written as x plus 5, that linear factor, multiplied by some quadratic factor, ax squared plus bx plus c. To find exactly what that quadratic looks like, I could find it by solving this equation by dividing both sides by x plus 5. These simplify out, and you see to find the quadratic, I can do polynomial division now and simply divide the given function by the factor x plus 5. So that process involves writing something here that when multiplied by the factor x plus 5, the first term would give 9x cubed. So that would be 9x squared, and when you multiply 9x squared by the factor x plus 5, you would indeed get your 9x cubed, you would get 45x squared, and in the process involves you subtracting that. 9x cubed subtract 9x cubed gives you 0. Then you have 27x squared subtract 45x squared. That gives you -18x squared. Then the process has you bringing down the next term of -79x, and then you repeat the process. What do I put here so that when you multiply it by the factor x plus 5, the first term needs to be -18x squared. So that would be -18x. And when you multiply -18x by the factor x plus 5, you would indeed get the -18x squared. Then -18x times 5 gives you -90x. Once more, the process has us subtracting those two things. -18x squared subtract itself gives you 0. Then you have -79x subtract -90x. That gives you 11x, bringing the 55 down. You notice that 11x plus 55 is divisible by the factor x plus 5. In fact, if I put a plus 11 here, 11 times the factor x plus 5 will give us not only the 11x, but also the plus 55. Now, when we subtract the two, we basically have an algebraic expression subtract itself, which gives you 0. The fact that the remainder is 0 proves that the factor x plus 5 was indeed a factor of the given equation. So now that I know that when you take the equation and divide by x plus 5, that the quadratic that you get is 9x squared minus 18x plus 11, that was the quadratic that I was looking for earlier in the video. So now we can say the polynomial given can be written as the linear factor x plus 5 times the quadratic factor 9x squared minus 18x plus 11. Now remember, the goal was to find the zeros of this function, so I'm still trying to find out when this is all equal to 0. So by the zero product property, when you have the product of two things and that product gives you 0, you can find the solutions to that equation by setting each factor equal to 0 and solving. We already have the solution of this equation. It was x equals -5. That was the 0 that we got by graphing. Now we can get the other two solutions by using the quadratic formula. So my a is 9, my b is -18, and for c I have 11. So let me throw those constants into the quadratic formula, and I see that I get the opposite of b would be +18, since b is -18, plus or minus the square root. B is -18. We are to square it and then subtract 4 times a, which is 9, times c, which is 11. And of course, all of that is being divided by 2 times a, and our a value is 9. Now you can do the calculation under the square root symbol, the radicand, and you find out that that radicand comes out to be -72. And our denominator is simply 2 times 9, or 18. let me break negative 72 into three distinct factors, the first of which I want to be a perfect square. The biggest perfect square number that I know that goes into 72 is 36. So I'm going to break negative 72 as 36 times negative 1 times 2. And since only one of my factors is negative, I can break this up into three radicals, square root of 36 times the square root of negative 1 times the square root of 2. Now simplifying my radicals, I have the square root of 36 is 6. I'll write the square root of negative 1 as I. And then I cannot simplify the square root of 2, so I'm going to leave it. Let me break the fractions apart by arguing that both this 18 is being divided by 18, and our other term in the numerator, this stuff, is also being divided by 18 as well. So I'll break that apart by saying 18 is being divided by 18, and then of course, since this division bar goes across everything in the numerator, the 6i square root of 2 is being divided by 18 as well. Then I finish simplifying by simply saying 18 over 18 is 1, and 6/18 can be simplified as 1/3. So I'm going to write my answer as radical 2 over 3, and that 3 in the denominator, of course, came from the fact that 6/18 is 1/3, and then I'm not going to forget to write the letter I. So here are my other two solutions. Non-real solutions always come in conjugate pairs, and you'd see that if you wrote this as two solutions, 1 plus radical 2/3 I, and 1 subtract radical 2/3 I. So my three zeros of the polynomial are x equals negative 5, 1 plus radical 2 over 3i, and 1 subtract square root of 2 over 3i. And notice that I've written all three of my complex solutions in the form a plus bi, and then x equals negative 5 is also a complex solution because it can be written as a plus bi by thinking of it as negative 5 plus 0i. The definition of a complex number is that it can be written as a plus bi, where a and b are real numbers. My a is negative 5, real number, and my b is 0, which is a real number. So I get my three complex solutions, which I was expecting because this was a degree 3 polynomial. Thanks for watching the video.